Welcome to Fire Protection Hydraulics and Water Supply. Today we're going to visit Chapter 1, and this is our introduction to hydraulics. So during this lesson, when we complete it, we want to define hydraulics and give an explanation of the origin and the science and history as it pertains to the fire service. And we want to understand the chemical and physical properties of water. Also understand the importance of mechanisms of extinguishment. We're going to talk about heat and the specific heat properties of water. And then we're going to look at calculate the needed flow or the volume of water that might be needed to extinguish a fire. And then calculate the volume and weight of water in containers of common shapes. So we'll start with the fire service hydraulics, and we know that fire service hydraulics began more than 250 years ago, and we even look back to early American culture that this is where in history everybody was required to keep a leather bucket in the household, and these were used for household chores and things, as well as that bucket had to be kept for firefighting purposes. And this is our first line of fire service hydraulics during the bucket brigades, as they were called. So it's very interesting history to read into when you get a chance. Hydraulics can be defined as the science of water or other fluids that are at rest and in motion. We realize that this is an applied science, and it is based on physics. This is divided into two primary areas or categories, which are hydrostatics and hydrodynamics. Hydrostatics basically is the branch of fluid mechanics that studies these fluids at rest and the pressure in a fluid or exerted by a fluid on a body or something that is immersed within that fluid. Hydrodynamics is the branch of fluid mechanics studies of the fluids that are in motion and that the fluid exerted by that fluid on an immersed body while that it is in motion. So the history in the fire service and the application of hydraulic principles began in earnest around 1889, and the fire protection and associated water distribution systems. And this is when, in a time when your water mains were nothing more than shallow ditches with hollowed out logs for water mains. And this kind of has evolved, over the years into the type of water systems that we have now. And if we look back on, again, history in the fire service, we look at the fire hydrant and why that we call a fire hydrant a plug. And this goes back to those early days when they needed to access the water main. They would basically chop a hole in it, and they would adapt their fire hose, which was made out of leather and riveted together, and then they would use that static pressure to get water and to draw water with hand pumps and that kind of thing out of their water main. Then they would plug it back with a wooden plug, and that essentially was your first access point. And it was a wooden wedge or a wooden plug, and so that's why you call your fire hydrants a plug, which is the modern access point now to your water supply. In 1910, the National Board of Fire Underwriters, or the NBFU, published the first fire flow recommendations and requirements. Fred Shepard is the champion of the fire service in this. He wrote Practical Hydraulics for Firemen in 1917. So we use water to help us extinguish fire. And we use water because water is very common. It is readily available in most cases, and it is abundant. And so we call water the universal extinguishing agent in the fire service. And so because we use water for many things and primarily extinguishment, we need to know a little bit about water. The characteristics of it, again, it is relatively abundant, it is easily stored, and it is relatively non-reactive. The chemical compound of water, as you may already know, is 2 parts of the element hydrogen and 1 part of the element oxygen. The water is also known as the universal solvent. The properties of water are it can be found in a liquid state as well as a solid and a vapor state. Water gets denser as it approaches its freezing point, and then it will get less dense right before freezing. So we know that water weighs approximately 8.34 pounds per gallon. Okay. In cubic inches, it's 231. It will absorb 9,343 BTUs and will produce about 227 cubic feet of steam per gallon. This is per 1 gallon. And so the specific heat ratio is 1 BTU per pound of water, and the latent heat of vaporization is around 970.3 BTUs per pound of water. So we get this steam conversion of 69,886 BTUs. At its densest, 1 cubic foot weighs about fresh water about 62.4 pounds. Salt water, we're talking around 64 pounds. 231 cubic inches per gallon that it takes up, and then 1 cubic foot contains about 7.48 gallons. And at its densest, water weighs about 8.34 pounds per gallon, and this is where we get the 8.3 basically for our water weight per gallon. Boiling point we know is 212 degrees Fahrenheit, and the freezing point of water is 32 degrees Fahrenheit. Triple point 32 degrees Fahrenheit at 0.08 or 8 100ths of a psi. For fractional purposes, it is non-compressible. So we need to know the boiling point. We need to know the freezing point because we're dealing with water on a regular basis. Freezing can be an issue for many different reasons of us using pumps, appliances, hose, trying to move water, and the boiling point at 212, we begin to make steam. And so by making steam and the steam dissipates out, we're taking away the heat side of the fire triangle. And by doing that, we are able to use water to extinguish fire. As an extinguishing agent, we talk in terms of the British thermal unit, and this is a unit of energy in the English system. The BTU is basically the amount of energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit at 60 degrees Fahrenheit. So technically, the exact value of 1 BTU varies marginally with the temperature. You know, if we have a higher or lower temperature, then that BTU is a little different. So the conversion of water to steam, this is important. This is something I would definitely dedicate to memory. You might see this on a test, but water expands to steam at the ratio of 1 to 1,700 times, and this is at 212 degrees Fahrenheit. So if we look at our conversion chart, or our table here on the slide, we'll see that this is directly proportional. So as the temperature goes up or increases, so does that ratio. And if we look here on the slide at 7,800, we're around the ratio, we're around 3,190 times per. And if we look again at the bottom of the chart at 1,200 degrees Fahrenheit, which we may typically have at ceiling height at times, we get that expansion of 4,202 times. So this is something to keep in mind as we're thinking ahead to spray water and get and greatly reduce heat. So water, we use it as a universal extinguishing agent. Two important extinguishing mechanisms are accomplished at the same time, and this is that the energy is absorbed from the fire, and then the steam generated then displaces the oxygen carrying air or tool for it as well. So this combination of both of these things is taking away a great amount of heat. The grayish white cloud rising from a fire is a cloud of water in a liquid state, and this is described as wet steam. So enthalpy, specific heat, and latent heat. With enthalpy, the total amount of energy contained in a substance, and that changes with the temperature as the temperature and the volume changes. So this is a thermodynamic quantity equivalent to the total heat content of a system. It is equal to the internal energy of the system plus the product of pressure and volume. Specific heat is measured in how much a substance heats up with the addition of a specified amount of energy or heat. For water, the specific heat is 1 BTU per pound. The enthalpy of water will change by 1 BTU as we raise or lower the temperature by 1 pound of water by 1 degree Fahrenheit. Again, they are directly proportional. Latent heat is additional energy, and it overcomes the energy bonding substances together. Needed fire flow, often abbreviated as NFF, this is the estimation of water basically that is needed to put out or extinguish a fire. Water is most efficient as a cooling agent if it is allowed to change phase and become steam. So we're looking for this steam conversion. How do we calculate needed fire flow? There's several ways to calculate it. Each has advantages as well as disadvantages to it. It is beneficial for pre-planning. An informal method to calculate the amount of steam needed to fill a room by excluding oxygen, the fire then cannot burn. And this is at 212 degrees. You got your 1,700 per pound that converts into steam, so it multiplies that volume. Now, an old Navy firefighting technique is to use the steam conversion in a compartment to your advantage, and that is where the original fog nozzle or fog combination nozzle was designed and put into place. And basically they would open up a door in a ship compartment where a fire was burning, and they would open up that onto a fog, a full or a semi-fog pattern, swirl it around, and then they would simply back out and close the door and let the steam, as it converted, do its job. It displaces the oxygen and then it quickly cools. So with the Iowa State Rate of Flow formula, this was developed by Keith Royer and Bill Nelson, where they say that 1 gallon of water could reliably produce 200 cubic feet of steam. They used the 200 cubic feet instead of the 227 to introduce a new margin of safety. And basically this knocks down fire within the first 30 seconds with a proper flow rate. And remember, gallons per minute is what puts out fire. You have to have enough gallons per minute to get the proper steam conversion to properly reduce the heat of whatever size fire. And this is why we're doing these flow calculations. This was developed, or then developed, the rate of flow formula as gallons per minute equals the volume divided by 100. And so the volume of the room is said in cubic feet. The National Fire Academy fire flow formula is one of the more widely used formulas, and the one that's out there, probably printed out there the most, I think. The more inclusive than the Iowa State formula. This is what a lot of fire departments are using in their building pre-plans. This basically considers the entire building, including its exposures. So in the NFA formula, it is length times width divided by 3 plus the exposure charge. Then we multiply the percentage of involvement. So you can guesstimate with this formula, do I have 50% involved? Do I have 25% involved? So on and so forth. And you can get a better estimate of the gallons per minute that it's going to require. Remember, with math, we need to do the order of operation, and that means we need to take care of everything in the parentheses first by order of operation, and then we move to reduce that and then what's outside of that formula. So this needs to be worked in 3 separate phases. Again, the base fire flow requirement, we calculate the area of the building and divide by 3. If a multi-story building is in play, we calculate the area of each floor and add them together. Take 25% of the base flow for each exposure. If there is no exposure, you don't need this step. If there are 2 exposures, for an example, then the exposure charge is 50%. That's 25% times 2. If you had 3, 25% times 3. Then we will add the basic fire flow and the exposure charge together. Multiply the sum of these two numbers by the percentage of involvement. The answer is the amount of water necessary to then extinguish the fire. Calculating volume and weight of water. The shapes firefighters should be most concerned with are cylinders, hose, water towers, and tankers are, in the cylinders type shape. Spheres, again, water towers, and rectangles, which is reservoirs and pools. And so we look at V1, V2, and V3 in this odd shape. So basically you figure in V1, you're figuring the volume of the rectangle, all right? In V2, we're figuring the volume of this 4-sided shape that's not a parallelogram. And so you use the formula of 10 foot plus 3 foot divided by 2. Multiply that then by 15 feet times, again, 10 feet. All right, so, and then we have to figure the shape of V3, the volume of that, as a square or rectangle as well. And then we simply add the 3 volumes together to get the total volume of a shape that's not rectangle or square. Formula for gallons of water in a given size container. Volume times 7.48. For a smaller container, find the volume in cubic inches, which is the volume divided by 231. Most problems call for simple calculations. The volume equals length times width times height, which the water in a tank on a pumper basically. On the cylinder, you can use this formula, 0.7854 times d squared times height, or the length of the cylinder. Most people use a guesstimation when it comes to cylinders. We're not going to get into, this using complex math on a scene. We need to know the basis of our volume calculations, but usually this is something that we've predetermined. We know what we're hauling as far as what's in our tanks and that kind of thing. To find the weight of a volume of water, we multiply the number of gallons by the weight of 1 gallon of water, which we said was basically or roughly 8.34 pounds. And so we can simply use this multiplication of the volume, or how many gallons we have, by the said weight of 1 gallon, and we're going to get that total weight to that total volume. If we only need to know the weight of the water in the cylinder itself, then we could use this formula, a little more complex, but one of the big reasons why we want to know total weight of water is if we know, or we can guesstimate about how much water we have flowed on a fire, and specifically we'll use the example of a structure fire, and we want to know how much weight that we've added to this structure, because on the safety side of things, when we add thousands of gallons of water, some of this water is going to run off and run out, but not all of it will. How much weight have we added to this structure now? And we find ourselves in the overhaul stage, and we could be in a dangerous situation when we have not allowed and caused water to run off and run out of the structure. Math and rounding. Fireground does not lend itself to the 2 decimal place precision. I mean, like I said, we don't need to be working out the math like engineers do down to the precise, because we're not in the practice of the precise science in our job. And in this case, we want to practice accuracy in the calculations that are not associated with the fireground. And this is, when we're talking about friction loss and we're figuring out preset pump pressures and those kind of things, that's where we want to be precise. We'll know those figures ahead of time, and we will know based on what hose and types of nozzles we're using and the length of hose we have and the brands and that kind of thing. We'll know those precise calculations ahead of time, and we'll know what the setter pump pressure is at. So develop habits that result in highly accurate, precise answers in this case. If you've developed a habit of accuracy, even the fireground can be more than a best guess scenario. Now, pump operators typically have pre-made charts where we have practice and accuracy. We have done the math in accuracy ahead of time, like I said. So we are doing this, and there's some different methods that we can figure out fire flow, but the National Fire Academy gets you precise. The Iowa one is a little faster, if that makes sense. Cautionary note here is in the text, older figures have been replaced with the results of recent calculations. You may see some older calculation factors and things like that in some text. The math basically is the same. It's your friction loss coefficients that have changed, and the reason that those things have changed is technology. I mean, we are making better fire hose. We're making fire hose today that has less friction loss because of the materials that are used for the inner liners of this fire hose, and so we're getting better and better friction loss. So you may see, older techs may have, or example, the weight of a column of water 1 by 1 by 1, older text would give it a weight of 0.434, calculated in the text to be 0.433 pounds. In different figures, if different figures have been used, calculations from which the figures were derived are also included. They give you the formula, they give you how they rounded these numbers up or down. So we've talked about what hydrostatics and what hydrodynamics are, how water is used as the universal extinguishing agent. We talked about Fred Shepard in the first book on hydraulics in 1917. The weight of fresh water, we've talked about steam, we've talked about steam conversion, and the weight of water itself. And we talked about the latent heat, the entropy of vaporization, the BTU versus the pound of water, and then we've talked about what the BTU absorbs as far as heat's concerned with that steam conversion. And remember that temperature and the water temperature, the steam, that this is directly proportional. As temperature goes up, there's a larger conversion. The NFF, or the needed fire flow, is the amount of water needed to extinguish a given fire. So this is where I want you to remember again, gallons per minute puts out fire. I want you to think of GPM. Gallons of minute per minute is what extinguishes and puts out fire, because the truth is we can have water. We can have water in motion through our pump. But if we are not applying enough gallons per minute for the volume and size of fire that we have, we're not going to achieve our goal of extinguishment. We have to meet that amount of water to put the fire out. Remember, water expands 1,700 times, going from 212 degrees Fahrenheit to the steam of the same temperature. All right. And then 1 gallon of water expands to 227 cubic feet of steam. So this is our summary for the first chapter. Hopefully everybody kind of understands water and how water works to our advantage.